Okay, so we just gave back test number 2. If you have individual questions about your test, just see me individually. Today we move on to implicit functions. I had said a couple of classes ago that we've learned our last derivative rule, right? Like we did, I don't know what the last ones were. Inverse tan or something was one of the last ones, and the natural log derivative. So we're done learning new derivative rules for specific functions, but today we get to learn how to take a derivative of a broader class of equations than the ones that we've done. In this branch of the course, like between test 2 and test 3, it is essentially lots of applications of the derivative. So like I said, we got no more new derivative rules, but we are going to see how to apply all the stuff that we know to different kinds of problems. I have just handed out 2 projects. These are the last 2 math projects of the semester, so make sure you grab one of each. And again, they'll be due in consecutive classes in a few weeks. Looks like right after Thanksgiving is when they are due. And I think that's it. Any questions on the calendar? Okay, so the first few pages of this packet we will come back to and talk about at some point, but not today. So we're jumping here on page 5. With our summary. Today, we learn the technique of implicit differentiation used when the equation for a curve is not written in the explicit y equals stuff with x format. So let's come down here and take a look at number 1. It says find an equation for the tangent line to that curve at the point -1, 1. So that curve has the x's and y's all mixed up, as opposed to every one of the other equations that we've played around with this semester where it's a y equals with things with x's in it, right? So the new technique is how we figure out how to take a derivative when the x's and y's are all mixed up together. And I will also point out that like the graph of that equation looks like wildly different from maybe any that we've ever seen before, right? Like it's got 2 pieces. One of them is like this oval thing, and then this like other piece that appears to have nothing to do with the oval thing, and yet somehow like that is the graph of a single equation, this one up here. Okay, so let's take a look at the point -1, 1. So we'll put a dot. -1, 1 right there. So is this thing that's pictured, is it a function? You guys remember a simple test you might have seen a couple of classes ago to decide if a graph represents a function? Vertical line test. If any vertical line hits the graph more than once, it is not a function. So this one clearly is not a function. But does it have a tangent line at this one point? Yeah. Right, there's a single tangent line. It's not, right, it's not that. That's not the tangent line. So go ahead and draw. Just, you don't even need a straight edge, just a real rough draw of the tangent line at this one point. You know, is it uphill, is it downhill, is it fairly flat, or is it fairly steep? So in this case, I think my tangent is something like that. Is that fair? So it's not clear how we're going to find that tangent line, but it has one, right? Like it doesn't matter to the tangent line that this is not a function. Okay, so the name of the curve, it's called a conchoid of Nicomedes. So this is a mathematician there. And we're going to take a derivative of the original equation, both sides with respect to x. So I've recopied my equation with just a little bit of space, and we're going to insert in this space derivative with respect to x on both sides. Okay, so far so good. It's legal because we've done the same thing to both sides. So we'll start on the left-hand side. What's the derivative of -5? 0. So we get 0 equals. Okay, now we're going to take a derivative of the complicated right-hand side. First thing that I see is the sum of 2 functions. So in my mind, they are separate and distinct functions, right? What's the derivative of -9x squared? It's -18x, right? Okay, I'm gonna tack something, that is correct, and that's the right answer. I'm gonna tack something else onto here though. I'm gonna say, suppose that instead of an x, this were just some other function. It was like 9 times some stuff squared, right? Then we could do a chain rule. -18, copy the stuff, subtract 1, but then times what? Derivative of the stuff. So I'm gonna write that, the derivative of the stuff. The derivative with respect to x, it's the same x as we had before, of the stuff. But what is the stuff? It's x. And so the derivative with respect to x of x is just 1, which is why we never write this. Otherwise, we'd end up writing this at the end of every single derivative we do. But I'm just going to put that there, even though it doesn't contribute anything. Then I'm going to copy my plus sign, moving on with the derivative. What derivative rule? This is a product rule, right? It's variables times variables. So product rule for me, copy the first times the derivative of the second. What is the derivative of x plus 2? It's just 1. But I'm again going to play this little game where I say, okay, you know, there's an x there. Any variable, my little radar is going off and says, okay, it's the derivative of the stuff with respect to x. So that x on the top is just copied from the x plus 2. Okay, but that was only part of the product rule. Now we do the rest of it. First times derivative of the second plus second. So now we copy the second. I'm running out of space here. We're going to go down this way. Copy the second times the derivative of the first. Yeah, so this is really just some stuff squared. X squared plus y squared is stuff, right? Stuff squared. So we'll bring the 2 down, copy the stuff. We subtract 1 from the power, so I won't write it, but it's a 1. Times the derivative of the stuff. Okay, now we're in the parentheses, x squared plus y squared. What's the derivative of x squared? It's 2x, but I'm going to keep playing my little game, or write this thing, which makes no difference. Plus, now we're looking for the derivative of y squared. 2y, but now it makes a difference. We were doing the derivative with respect to x. That has been the same throughout. But what's the stuff in this case? It's y. And so that right there is the only new thing for this problem. It's the only new thing for today. Is that dy dx is the chain rule. All of the dx dx's you don't need to write. But I want to put them there so you don't feel like we're treating x and y any differently. We're not. We're just, every single one of these is a chain rule, and you always end the chain rule with times the derivative of the stuff. If the stuff is simply x, then the derivative of the stuff is 1, and it's silly to write dx over dx. But if the stuff is y, it's a fundamentally different kind of creature than x. And so I'm imagining, even though this is an equation with x's and y's all mixed up together, I'm imagining like maybe I could somehow solve this and get y by itself. And so I'm imagining in my mind y equals and then some crazy equation with only x's, no y's. And so if I had that crazy equation and I said, hey, you know, what's the derivative of y squared? Well, you would say, hey, instead of y, let's put all this crazy stuff with an x in it, right? And it would just be all this crazy stuff squared. And so you'd say, oh, 2 comes down, copy the stuff, subtract 1, times the derivative of the stuff. Well, I don't know what this stuff is because I can't solve that equation for y. But the derivative of y has to go here. The derivative of the stuff has to go here. Okay, so let's write this again. But I won't write all of these silly dx dx's anymore. So we go 0 equals negative 18x, and then that's just a 1, plus x squared plus y squared times, and that's just a 1, plus x plus 2 squared, thank you. Plus x plus 2 times x squared plus y squared times 2x, I won't write the dx dx, plus 2y, but you have to write the dy dx. Okay, remember the goal here is to find the equation of the tangent line. And in order to find the equation of a tangent line, we need the slope. And we know that the slope is the derivative. So on the one hand, we could solve this equation for dy dx. It actually would not be terrible to solve for dy dx. Just imagine for a second what it would look like. The minus 18x would need to get added to the left-hand side. The x squared plus y squared squared, that needs to get subtracted to the left-hand side, right? So we're just building some things over there. And then I think what we'd have to do is maybe distribute all of this through the 2x plus 2y, because I need to unbury this dy dx. I need to get it out of the parentheses. So the way to do that would be to distribute. And then I just have a lot more other stuff up here that doesn't have the dy dx in it. That would all get added and subtracted to the other side. And then finally, I'd have one little thing here with which has a dy dx times some other things, and I would divide by that other thing. So I could solve for dy dx. We're not going to, but we could. Yeah, Daniel.
Could you, once you move the
yeah. Yeah, that's another option, right? Divide both sides by that after we've done our adding and subtracting. Divide by that. And then we'd have this, subtract the 2x, divide by the 2y. You'd have fractions within fractions. It's okay. Yeah, totally valid.
So we can, I mean, it seems weird.
It won't be 0 for long. You're adding 18x, so it's not going to be 0 anymore. Yeah. 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 Yeah, 0 divided by anything is still going to be 0, and that's totally fine. Yes, there's a problem to divide by 0, but it's not a problem to do 0 divided by. Yeah. Okay, so you could solve for dy dx. What would be unusual is that the dy dx equals would have not just x's in it, but also y's in it, right? Every other derivative we've had so far this semester says dy dx equals, and it's only x's on the right-hand side. Well, we can't do that anymore. This one would have y's in it. But the point isn't to find the generic derivative formula. The point is to find the slope of that one tangent line. And at that one tangent line, how much is, well, we have a point that's on that tangent line. What are the coordinates of that point? Negative 1, 1. And so we can replace x and y with negative 1, 1 at any point, including right now. And that's what we're going to do. So substitute x comma y equals negative 1 comma 1. So let's try that. 0 equals negative 18 times, how much is x? Negative 1 plus x squared. That becomes negative 1 squared plus. Next one is y squared. What is y? 1. 1 squared. That whole thing is squared plus. Okay, if you understand what we're doing here, then it's better for you to look at your own paper and not at the board. I'm going to keep writing it, but you keep writing yours. All we're doing is substituting x and y becoming negative 1 and 1. dy dx is the only thing we're not substituting. Okay, so we've got everything substituted. Now we're ready to just start doing some arithmetic up here. So 0 equals, let's see, I see negative 18. How much is in the parentheses? That's a 2 in the parentheses, right? Negative 1 squared plus another 1 squared. So that's 2. 2 is getting squared. That's plus 4. Plus, how much is in the next parentheses here? Yeah. Oh, positive 18. Thank you. Making lots of mistakes here. My back is really hurting. So what I'm focused on is like walking very gingerly, like left and right. And so I can't do like negative 1 times negative 18 while I walk gingerly around. Okay, so we got that. How much is in the next parentheses? 1. That's the 1 times, I'll copy the 2, times how much is in this parentheses? That's a 2. Okay, and then finally, negative 2 plus 2 dy dx. Okay, so it's looking a lot better after just one round of cleaning it up. So let us keep cleaning it up. 0 equals 18 and 4, that's 22. 2 times 2 out here, that's a 4, and then I'm copying the stuff in the parentheses. Okay, so remember, the goal is to get dy dx by itself. That's what we're going to figure out the value of. And whatever we get is going to be the slope of that tangent line. So this is pretty straightforward from here. So we will subtract the 22. If you want, you can distribute the 4, or you can do the thing that Daniel had suggested. You could divide by the 4. I'm going to distribute the 4 here. So negative 8 plus 8 dy dx. And again, trying to get the dy dx by itself. So what goes next? Add the 8 to both sides. So we get negative 14 equals 8 dy dx. And then divide both sides by 8. So dy dx equals negative 14 over 8, negative 7 over 4. Does that slope jive with the tangent line you drew? Does it look like it could be a slope of -7/4, like -1.75? Yeah, right. Something negative, fairly steep, but not incredibly steep. Okay, that makes sense to me. Don't forget this equation, this problem didn't say find the slope. What did it say? Find the equation. This is something else a few folks stopped early on the test. One of the questions said find the equation of the tangent line, and a bunch of us found the slope, which is great, but a few of us stopped right there and didn't find the equation of the tangent line. So how do we do this? So y equals mx plus b. You know the y value at the point is how much? 1 equals, we just found the slope after all that hard work, -7/4. How much is the x value at the point? -1. And then the b we are about to find. -3/4. Is that okay? Is that right or no? Multiplying by the reciprocal would have an undesired effect on this b. You want to subtract the 7/4. Yeah, like you would have to have a 4/7 on your b as well. Yeah. Okay, so then I think we've got the equation of our tangent line. Y equals, we said the slope was -7/4. Yeah, and then x, and then plus the b -3/4. And does that y-intercept jive with what you drew? It looked like the y-intercept was maybe just below the origin. Yeah. Okay, so that's how we do it. Even if the equation has x's and y's all mixed together, we can still find the equation of the tangent line. Yeah, that's a good point, is that on the test, I didn't tell you what the y was. It just said find the equation of the tangent line at x equals 2 or something. And so you'd have to go back up and find the y. I can't ask you to do that here, because if I tell you x equals -1, well, the y is really buried inside of here. This one I think we could do, but it's really easy to make equations that we can't solve for y. Yeah. Okay, so the only difference when we take a derivative here between all of the derivatives we've done this whole semester is that when you take a derivative of anything with a y in it, you bring the chain rule out and you multiply by the derivative dy dx. So the only place that this mattered was right here. What's the derivative of y squared? It's not just 2y. It's 2y times dy dx. You see the chain rule there? If I can jump ahead, for example, coming over here, this is one of the, hang on. Coming over here, you don't need to turn the page. This is just one of the even more practice problems. But what is the derivative of 4y cubed? It is not just 12y squared. What is it? It's 12y squared times dy dx. Okay, every single thing that has a y in it is going to have a dy dx. When you do the derivative of xy, what rule is that? That is a product. Looks really simple, but it is a product of two variables, x and y. So when you do the first times the derivative of the second, first you copy the x. What's the derivative of y? It's not just 1, it's 1 times dy dx. Okay, I think that's good there. All right, so we're going to spend just a few minutes looking at Geogebra right now. I'm going to spend these few minutes because I think Geogebra is really cool software because it has sliders. It's one of the nice things about it. So if you're using some other software, as long as it has sliders, you can do the same kind of experimenting that we're doing here. Geogebra is free. You can just Google it and find it. So this is just how it looks when you start. I'll make the font size bigger so we can all see. And I'm going to start by making some sliders. So take a look. I'm going to need somebody to read that equation to me in just a second, but you can see it's got an A and a B and a C. Compared to the equation that we actually just played with, how much is the value of A? 0. And how much was our B? No, that was before. It was -9, right? That was the value of B. And how much was our C? 2. Okay, so then I've just replaced those three particular numbers with these sort of more generic parameters. And so A, B, and C, I'm going to make sliders. Here we go. So we're just going to click this button right here. It says slider. You just click anywhere in the blank, and it says, okay, it's going to give you a slider where the values of A go between -5 and 5. A was 0 for us. Or how much was A? Was 5? No, it wasn't 0. Wasn't it 5? -5? Okay, so I'm actually going to go, yeah, -5 is fine. And then, so all that does is give me this little thing where I can drag it, and at the far left, it's -5, and at the far right, it's +5, and it just slides in between, okay? So that's A. So I'm going to set this one at -5 because that was what we had in our equation. And then I'm going to do another slider right below it. This one is B. You said the value of B was -9, right? So -5 to 5 is not going to capture it. So you can make any numbers you want here. I'll do -10 to 10. And that's fine there. And then our C was, you said 2 or -2? 2. Okay, so -5 to 5 is fine there. All right, so I've got my, my 3 sliders all ready to go here. I'll set these up so that they are on the same numbers so that it looks like our graph. So I think -9 was this one, and then +2. Okay, so all we have to do down here is type in the equation. So I need somebody to read that equation. So it's A equals, X plus C. Okay, there it is. So that is the graph that we were talking about. And the nice thing about the sliders is that I can just make a change to one of these parameters, A, B, or C, and see immediately the effect. So remember, A was our left-hand side. It was -5 before. So I'm going to make this a little bit bigger, and we're going to see what happens, if anything, to, sorry, make this guy a little bit bigger and see what, so what's happening. So the left-hand guy is kind of like getting like bigger, and the right-hand side. So now what's going to happen, right? It's like, oh, yeah, right? So something's about to happen, right? These two things are about to like fight with each other. So any guesses what's going to happen? Merge. So how many pieces are we going to have? 1. So look at you guys. Look at you guys. Yeah. All right. The -9, that was the thing in front of the first X on the right-hand side. Okay, so let's see what impact that has. Oh, well, we just lost our friend there on the right-hand side. That's too bad. Yeah, that was sudden. And I was thinking like maybe he would appear on the right-hand side, you know, like the mirror image, but on the left-hand side. But no, apparently he only, yeah, we're just like there, and then right. So something's happening at like -8.2-ish. Don't know what's going on there. And then so what was the other one? Was the C. So what happens if we do this? And the guess is what's, look at that. Yeah, I think Stephanie's lava lamp analogy, that was a good one. What is happening here? And so this is complicated, right? Like this graph is way more complicated than any that you would study in a pre-calculus class. But this technology makes it so that you can play around. And, you know, like we've only messed around with them one at a time, but maybe change this guy to that number and then start seeing what happens here, right? So anyway, so I encourage you to play if you're into that kind of thing. I think the software is really great. All right, I think that is it. So the idea here is that you're using this technique when the X's and Y's are all jumbled together, and you'll see a bunch of them in the activity. All right, so let's jump in and see how far we can get.